meters, and Hungary challenging Taiwan. And you can challenge on problems 2, 3, 10, 14, and 17. It's written there as well. Yeah, you start the challenge clock. And
so we would like to challenge you from problem number 3, Lato Lato.
okay. Problem number 3, Lato Lato, etc.
Yeah.
Problem.
I think I like this problem.
And please write down the name of the recorder.
representing problem number 3, lato-lato. If we attach a ball to each end of a string and then connect the center of the string to a pivot, when a pivot oscillates along the vertical direction, the balls will start to collide and oscillate with an increasing amplitude. We ought to investigate this phenomenon. First, it is important to know that the motion of the lato-lato can be separated into parametric resonance and collision. This is an overview of my report. Let's start with my setup and equations of motion. We use a reciprocating machine with hamstrings of different lengths. The relevant parameters include the pivot's frequency, amplitude, the string's length and damping ratio for parametric resonance, the ball size and the coefficient of restitution for the collision between the two balls. So let's dive into our theory. Let's first talk about the gravity modulation by the fictitious force. Under the inertia frame, we can first assume that the motion of the pivot can be estimated as a simple harmonic. We can then, through second derivative, get the fictitious force, thus the effective gravitational acceleration. We can then consider the condition for string rigidity using the relative acceleration. We can separate this equation into 4 quadrants using the acceleration and the amplitude. We can denote that the only quadrant 1 and quadrant 3 satisfies our equation of motion. So we can then consider the finite size of the ball and get our equation of motion for the single pendulum, accounting for the gravity modulation and damping. We then consider the inelastic collision after a single pendulum motion, calculate the collision condition using the arc signs, then we set the initial conditions according to our coefficient of restitution. We then discretize the whole process using Euler's method. We then move on to characterize the damping ratio of different string lengths, and also the coefficient of restitution. Next, let's move on to my qualitative explanations. In my experimental data, we can see as the frequency ratio match reaches to 2, we can see a clear increase in the oscillation amplitude. While at exactly 2, the system damps out at the resonance breaks, demonstrating a frequency ratio match of the system. For the phenomena explanation, we have observed at the pivot's highest point, the two balls will collide, and at the pivot's lowest point, a large angle will occur, demonstrating a phase difference in the phenomenon. Well, this is due to parametric excitation, where we can consider a gravity modulation. In the pivot's first half cycle, the gravity is larger than usual, and thus it couples with a large sine theta to maximize the work done into the system. While the opposite effect can be seen in the pivot's second half cycle, minimizing the loss. So both the positive work and the negative work will increase at resonance conditions. So we can plot the potential fields of the system. This is the original pendulum potential. Accounting for the gravity modulation, we can see that the trajectory of the lato-lato ball aligns with the gradient of the potential. So the energy gained from the pivot's kinetic minus the energy loss dissipation will equate to the energy needed to overcome the field. At resonance, this increases. So we can write down the energy formula as this. And this, we can see a convergence of these and a dissipative of this. So a steady state may be possible. We can then move on to the amplitude fluctuations of the system. This is the data from our experimental video with the theory. We're taking the discrete Fourier transform, we can see multiple peaks forming. This is due to this motion being a complex harmonic. Zooming in to this cognitive beat, we can analyze the amplitude oscillations of the system. We then fitted a damp sign of 0.207 Hz, which is same as the difference between the driving frequency and the natural frequency, demonstrating that the ball is moving at these two multiple modes. We can then classify the two phases with the oscillating phase and the stable phase. Plotting the phase space diagram, we can see a limit cycle forming. This demonstrates the orbital stability of the system, where the amplitude increases with a plus and minus epsilon, as the epsilon will converge to the energy steady state that I have previously mentioned. We are also able to obtain a Foucault multiplier smaller than 1, indicating a stable orbit. We can then move on to investigate the stable state oscillations after we have done the experiment for a long time, plugging in the initial conditions, we can see a good quantitative agreement. Well, this is due to an asymmetric collision point oscillation, which we can actually see in our stable state frequency, where there is a new peak that is not a harmonic. This is because the center of mass of the pendulum ball will actually oscillate like a simple pendulum, thus giving us this new frequency. So now our equation accounts for the asymmetry, gravity modulation, and the damping. We can then analyze the stable state frequency. We can see that the energy insertion roughly equals to the energy dissipation, with the inelastic collision being the main source of dissipation in this phenomenon. Next, let's move on to my dynamical driving frequency. At a driving frequency, there will be a resulting amplitude. This is called a jump resonance. When we increase the driving frequency, the resulting amplitude will decrease. If we then decrease the driving frequency, some previously not possible amplitudes become possible. This is because the energy is sufficient to maintain the system, but not sufficient to initiate it, demonstrating a hysteresis in the system. This is our experimental verification using a 25 centimeter string. The same effect can be seen with 45 and 35 centimeter strings. We can see that the resonating amplitude slightly increases from 2 times the natural frequency. Well, this is because the ball size deviated from the original parametric resonance. We can then investigate the effects of the string length. For small angles, the angular acceleration will be proportional to omega 0 squared. If we assume that at the stable state it is close to a sine function, this should be a cubic function. While for a simplifier and explanation, at 25 centimeters, because the string length is very small, thus has less gravitational potential, so it can reach greater amplitudes. So lastly, we can plot a phase diagram with the O reaction, hysteresis, and the no reaction region with the string length and the driving frequency. We can then denote the increasing amplitude of what the problem statement had mentioned when we move from this region into this region. Well, this is an increase in the omega 0, making the initial conditions of initiation with a larger frequency. Next, let's move on to my further insights. With different driving frequencies, we give it a range of initial conditions. We then ran the simulation for a long time until a steady state was reached. We can see multiple steady states forming. This is due to the possibility of multiple oscillations per collision. Well, this is the half bifurcations of the system, and this is the resonance. However, if we plot the experimental data, we can see that only k equals 1 is experimentally observed. This is because of the string condition that we have previously mentioned. Calculating the parameters, we can see that after a bigger frequency than 3.94 Hz, a stacking will occur, thus making the other steady states not possible in those strings. We can analyze the stacking movement on why it makes the increasing amplitude not possible. At a very high acceleration, the string will accelerate with multiple g's. Here, the string does not have enough time to accelerate, and at this negative acceleration, the ball will enter free fall, thus the ball will dance, making the increasing amplitude not possible in this situation. However, we have investigated the phenomenon with the fixed steady states. In our state, we can see that there are multiple oscillations per collision, which is our further insights. Next, we have investigated the phase 2 by our hands. And if we can denote the two phases by the phase 1, where we reach a stable state by slowly sinking the frequency, and the phase 2, where we suddenly increase the oscillation amplitude for a double collision. This is our experimental data from our hands. We can see that in phase 1, the amplitude are relatively consistent. And at phase 2, we suddenly pull down the system and make it reach. So we double collide, so the amplitude will no longer increase. We can then plot the phase transitions of the system under different amplitudes. This is the region where our EOM is invalid. And this is the region where we can move from phase 1, and after a sudden amplitude jump, go to phase 2. Well, the opposite direction is not possible due to hysteresis. So for the explanation, at quadrant 1, when the ball is reaching to 90 degrees, through a sudden pull, this amplitude will reach a negative value, thus making the string turn again. So it will safely reach to quadrant 3, getting a double collision. So this is a summary of the phases. At quadrant 1, only a single collision will occur. At quadrant 2, the string stacking will prevent the other possible steady states from happening. At quadrant 3, a double collision will occur when we suddenly increase the amplitude. And at quadrant 4, a phase failure will occur when the ball reaches larger than 90 degrees. So for the conclusion, we have classified the lateral motion into 2 parts, including parametric resonance and inelastic collision. We have also explained quantitatively through coupling and the potential field on why the resonance will occur. We discretized the theory using Euler's method and find an excellent experimental agreement. We then explain the amplitude fluctuations and find the frequency of multiple modes. We also found a jump resonance in the system and verified the hysteresis experimentally. We plotted a phase diagram to explain how the string length affects the phenomenon. Lastly, in our further insight, we got the bifurcation diagram on the steady states of collision, and the phase 2 transitions was also discussed using the string's boundary conditions. Here is the total overview of my report, and thank you for listening.
Thank you very much for your presentation. I would like to start with your setup. So, were the balls fixed on your string, or could they move?
They are attached to the ball.
Yes,
so
but can they move on the
string.
string?
You mean the ball tilt?
No, can they move along the string? So
No, they
change
cannot.
string length. Okay. And why is your damping ratio different for different string lengths? Or how much do they differ?
Well, I believe that it does not differ very much, but we wanted to make the simulation
okay,
more
but
precise.
how much does it differ? Can you please give me a number?
I believe that.
Okay, then let's just script. Did you measure air resistance?
Yes, it is characterized with the damping. This is the viscous damping.
So this damping is for both the air resistance and the collision.
No, we have separately considered a coefficient restitution and the damping ratio. The damping ratio is the air resistance, which we have characterized using a simple pendulum.
Okay. And would this? Okay, thank you. And so, what do you define as the natural frequency of the lotto?
It is the natural frequency of the oscillations. This single pendulum oscillation.
And can it only? So, if we look at the lotto as a simple pendulum, that would be the natural. Okay. We will discuss this later. What is the difference between the oscillating and stable phase?
You mean? The oscillating is when the amplitude is increasing, and the stable phase is when the amplitude no longer increases
thank you very
and
much
reaches
for
the
that. And what needs to happen for to have a phase 1 in the first place? So to have a downward collision.
Well, I believe there will be small perturbations when you first move the ball, thus causing an initiation, which causes the hysteresis.
And did you include slacking of string? Did your string slack in your simulations?
We have considered the string conditions in the simulation, which will cause the phase transitions, which I have mentioned earlier.
Okay, thank you. We will discuss it.
Thank you. Preparation time, please.
lotto. So the task is to attach a ball to each end of the string, take the center of the string and oscillate in the vertical direction. The ball will start to oscillate with increasing amplitude, and it was tasked to investigate this phenomenon. Now, the theory was based on gravity modulations in an inertia system. The explanation was visualized by the potential hills with the collisions and the amplitude increasing. The experiments were done with a contraption which tried to limit the movement to one plane. But there was some movement out of plane still possible even with this setup as visible in slide 2. And there were very few measurements. Comparison to theory with experiments had no error analysis. So for the increasing amplitude, the oscillations were explained really well, and the phenomenon was also explained really well, and how the system behaved was looked at in very much depth. But what I was missing is having a very basic, very intuitive first answer of why we can see any oscillation, any increasing amplitude in the first place. For the forcing behavior, the motion was investigated, but not every parameter was measured. But so you didn't show as many measurements, you prioritize your theory. So for example, the material of the balls, which would of course change the coefficient of restitution, or different the ball size, which would of course then change air resistance, and also the radius, which would change the frequency. The collisions were looked for in a symmetric and asymmetric case. I thought it very impressive that it was looked at in an asymmetric case as well, so I think that was very well done. And the boundary conditions were investigated from phase 1 to phase 2, but I would like to see more for phase 1. So the strengths were, the advanced equations were also very well explained. The parameters were also looked at, and the visualization was very good and made this complex phenomenon easy to understand. Also, I really liked the potential here, the energy landscape you had, that was very nice. And the setup seemed to be working on a good level. We will be talking about this later. Then the comparison for what was done was there and done well. I would have considered some more parameters, for example, the amplitude of the forcing behavior, as well as the string length and the string radius, which I think is very crucial when we're talking about the frequency of it. Also, the conditions to phase 2 were discussed, could have been discussed more in depth, especially in respect to the string, which I think we will be discussing. And also, I would have liked some more measurements, because the theory was very well based, and I would have really liked if the measurements could then back-to-back just support that. And also, I would have liked some more error analysis. So overall, I really like the explanation of the phenomenon. It was done step by step and thoroughly. The theory is also very good, and the experiments was where it was lacking for me, and the comparison of then the theory and the experiment. And now I would like to invite you to a discussion, and I would like to start with slide 2, please. Could we look at the video? Yeah. So this is a rod inside another cylinder. Can you just describe what this contraption up there is we can see?
So as you can see, we actually use a different experimental setup. That is just the observation video. We use this setup for the rest of the experiments. This is a reciprocating machine, which we have to turn the upwards to make an oscillation. I believe that this has a very good control of the vertical movement. And I don't believe that there will be a plane movement that is due to a lack of experimental control.
And the turning up and down was done by hand.
What turning up?
So this is
done with a motor with 0 to 4 hertz.
Thank you for the clarification. And can you change the amplitude of this?
Well, it is possible to change the amplitude.
Did you?
We have investigated that theoretically, where if the amplitude is too large, there will be a phase 2 transition. However, I don't think it will be possible with that experimental setup, because we cannot dynamically change the amplitude for it to reach the phase 2.
I agree with him on this, but can you tell me what frequency this was here? So this is the maximum swing amplitude of the amplitude of the pivot on the y-axis?
No, this is the amplitude of the ball.
Amplitude of the balls. Okay, and what frequency are we looking at here?
I think that this is close to the natural frequency. I
Natural
believe that's
frequency.
2.2.
So you're saying that for a, so what is your conclusion then on this? So as we,
I think that the amplitude will increase, the pivot amplitude will increase the swing amplitude due to an increasing energy insertion into the system, which if you plot the potential field, you can also see that the gradients will become a more, with a bigger slope. But if it reaches to a certain condition, a phase 2 transition will occur and making it not possible to initiate in the machine setup.
okay, thank you.
Thank
So I see that he has looked at the amplitude, and I think this is quite important. So I am happy to see this. But what I would, if you already introduced the topic of phase 2, I would like to ask, what are our conditions for transition to phase 2? So we say amplitude, but are there other conditions we have?
Okay, so I think I have stated it pretty clear in my report, is that when we are playing the lato, we first like slowly, you can see the video, we first slowly sync the frequency so that you have like a stable state. Then we dynamically increase the amplitude for it to reach the double condition.
But can you give me some quantitative, boundary for this?
Well, the quantitative boundary is the jump between this point and this point, which we can see. And there are
So, but if I told you I now want to phase 2, could you produce it for me like this? Could you give me for if I said I want to phase 2, could you tell me what amplitude and what frequency I needed?
I believe that will be possible because this amplitude we investigated is the amplitude we use with our tanks. However, there might be a boundary condition right here.
Yes, and what do you think the boundary condition could be?
I think it will be like 5 centimeters for this.
No, but I want to go into the physics of it. So if we wanted to have an upper collision, what would need to happen? Of course, the ball would have to move above the pivot, and for this to be a collision and for it to not fall out of its trajectory, the string needed to be pulled taut. It needs to be not slackened, and for that you could potentially put a boundary.
Yes, the boundary condition can be characterized via this equation, where this will be smaller than 0.
Okay, so I do see that he has an understanding of it, but still, I do think that it would have been interesting to have an actual quantitative, just an equation based on the physical properties that showed us when a transition to phase 2 would be possible, but I'd like to move on. So this problem is about the increasing amplitude.
Yes.
And so you define the natural frequency as the frequency it would have as a pendulum.
Yes, it is the frequency of a normal oscillating pendulum.
And would this still be true if the radius of the ball would increase?
Well, I believe that it will still be close. However, we have considered the finite size inertia of the ball. So I don't believe that will be the case.
So, but you see, this entire system is described by a second-degree equation. So it will be very, very sensitive to our initial conditions. And if the natural frequency of the lotto is different,
I believe that it is not sensitive to the initial conditions because the flow K multiplier is smaller than 1, thus indicating a stable orbit.
So do you think, then this leads me to an next question, do you think there will be chaos in this system?
Well, I don't think so if the string is taut. So
If the string is taut,
yes, if the string is taut under a certain magnitude of frequency, which we have discussed, the boundary of the stacking, then you will not pursue chaos because
and
the string is
in
always
your
taut.
entire work, you assume that the string was always pulled taut.
Well, because if it isn't taut, which will indicate other possible steady states and make it not possible, because you will. I have actually investigated in my
Okay, but then let's please, can you call up the slide where your ball is whipping past the, where it's the symmetric case, when it's like swinging over the center of mass is swinging over the string.
You mean this
I'm sorry, I'm not quite sure what
the stable state?
Yeah, so here we can clearly see that the string is not pulled taut the entire time. And so I do understand.
But first, I would like to clarify that there is a difference between the string wave and the string snap. The string wave is caused by the sudden impulse into the system, thus causing a wave-like phenomenon to form on the string, which I think that it has a minimal influence on the phenomenon due to a good experimental agreement. While the string snap is because the acceleration is too big for the tension to occur, making the tension zero.
Okay, but for us to have I agree with if we're describing a stable phase one oscillation, so we have only one upper collision, of course we have to assume the string to be pulled taut. But if we look at the whole phenomenon being activated in the first place, and for us having collisions in the first place, there the string needs to be pulled taut, and therefore in your entirety, just assuming that your string is always taut will not even.
I have investigated the boundary conditions
But
using
it's
the
not a
phase
boundary
position.
condition though. I understand that you have, but it's not a boundary condition. So if we want to have a oscillation in the first place, what needs to be done is that these balls will need to collide in the first place. And you cannot have this collision as the string is just pulled taut, because if it is pulled taut and you move it up and down, it will just move along with it.
Well, I think you are referring to the initial conditions of the system. If we initially give it a perturbation, then the energy
Yes,
insertion
but you
will
need
get
to give it
amplified.
an initial perturbation.
Well, I
This is
think
my
this is
point.
caused by the string wave rather than the stacking of the string. Because the stacking of the string is when the tension reaches zero.
So I don't think that we're finding common ground here. I understand that when we're describing the movement with just one upper collision, we will assume that the string is taut, because otherwise it would just be a very hard to model. But in order to understand the basic phenomenon of why we have this, we need to acknowledge that there is such thing as the string not being pulled taut. But I would, and this is then at this point we can also not look at knot chaos. And I would just like to show again that in order to have a collision in the first place, the strings do need to slack, as you can see. So it's not possible.
Oh, I can understand.
But I'd like to
I think
move
I
on.
have
I think we
investigated it
spent a
using
lot
the
of time. We
hysteresis.
spent a lot of time. I think we agreed to disagree.
Thank you.
So I would like to go back to so what do you think would happen if your ball was elastic, so it could deform?
I believe that the coefficient of restitution could also be characterized if it is under
So
that
it would
case.
change the coefficient.
It will change the coefficient of restitution.
I agree with this, and I think this could be measured. And what if the string would be the one that is elastic?
I think that the string here, if the string is elastic, it will get pulled longer if it is oscillating. Thus, I think that because of the asymmetry, will make the initiation much harder for the machine and the hand.
So you think that so to have a oscillation with just one upper collision?
I'm not sure what you are referring to.
So, what do you think, in your theory that we've heard understood, would change if you assume the string that is elastic?
So for elastic string, will it like deform and get smaller
So
and
it can
longer?
deform, it can plastically deform. You know, or not plastically, it can
Are you suggesting using like a rubber band
Exactly.
to make
For
the
example.
it will make the initiation harder?
Yes, but do you think theoretically you could still have this? So you could still produce
I
it?
believe it will determine how elastic the property is, because you are just giving me a qualitative talking about the
So, but
elasticity.
you agree that it could work?
It is possible to work because the string has minimal elasticity, low still process.
So I do think that it could work. However, as we saw, this first slacking of the string is very chaotic, and it's kind of probabilistic when it will start stabilizing. And I do think that it would be in reality not able to produce this movement with a very elastic string. And I would like to thank you for the discussion.
Summarize.
And so we talked about the experimental setup, and we talked clarified some things about the setup, and overall just explaining the effect and examining phases 1 and 2. So for phase 1, I think that while the reporter has a great understanding of stable oscillation, he could not give us an explanation as to why we can see this phenomenon in the first place, and also he could not give us a boundary for phase 2, whereas I think he showed a great understanding, but he still, for some reason, didn't write a condition for entering phase 2, which I think would have been very important. important. Also, we talked about the elasticity of the string and how it would change it, and we talked about chaos in the system. And I do think that these topics are tied together because as the elasticity of the string changes, it also becomes more chaotic. Thank you for your attention.
Thank you.
So, I would like to start with the question to the reporter. Do you think that for the second mode, where the balls are also bouncing at the top, it is important that the hand is giving feedback from the movement of the balls, or it can be done by a motor or machine?
I think that it has to satisfy a dynamical amplitude change. Though I'm not able to design a machine that can do that, but I believe that if a machine can satisfy a condition of dynamical changing at a certain time frame, then it will be possible to do it by the machine.
Opponent, do you agree with that?
So I do think that it's always a play of the amplitude and the frequency. I think for a higher frequency, the change in amplitude does need to be that large because at the end we're looking at the vertical routine.
Okay, thank you. Now I would like to ask the opponent why she thinks that the balls of the lato-lato have to be attached at the string.
At the string.
You asked it in the questions that the balls if the balls of the lato-lato are.
Also, because the string length could potentially change if the center of mass of the ball moves up along the string.
Okay. Now I would like to ask the reporter if he somehow measure the deviation from the harmonic movement of this driver or the pivot.
You mean the oscillating driver?
Yeah. If you try to measure if it was really harmonic.
Yes, we have measured it and we have fitted a sine curve to know that it is harmonic.
Okay.
It has a coefficient of determination of 0.98, if I remember it correctly.
Okay. Next question. Do you think it is the initial condition of the lato-lato is important for the state at which it stabilizes?
No, the initial conditions will not change the stable state.
Okay. So, when you have some in the graphs where you make your measurements, do you make any statistics for the measurement of the stabilized amplitude? For example, when you have a graph depending on the frequency, or it is just one measurement for the.
What do you mean by we take it? What do you mean? What measurement? The frequency, the amplitude, or?
You measure the maximum, the stabilized amplitude, right?
For stabilized amplitude, we make the experiment go for a long time and find like the final amplitude of the experiment.
And you do it just one time, or do you resist?
Because we do it for a long time, we can actually find like the largest at the final position, so it has no error bars.
Yeah, okay. Did you somehow?
You have time.
Sorry.
You have time. You can ask. You can early. You can ask the question.
Did you somehow try to? Or.
Thank you very much.
Because it's not related to
I'm Kaspranda from Czechia, and I will be reviewing the task number 3 auto. So let's start with the summary of the opponent. The reporter presented a working and repeatable experimental apparatus for the lower mode of the auto, but didn't make any apparatus for the higher mode of the auto, which we think is good but not perfect. He described he gave a phase diagram of the auto movement, which we think is a really interesting visualization of the data, and he mentioned the hysteresis in the system. We believe exists, but we think it interferes with the initial condition he is giving to the auto. When the reporter is using the Lato machine, it's doing something like this, but to start it, to not just look like this, he has to give it some initial condition. And depending on the initial condition, the system gets some energy, and so it changes the cutoff for the hysteresis curve. So there can be some improvements done for this. Now to the summary of the opponent. Opponent had many good points and clarified the presentation of the reporter a lot. She mentioned the initialization of the Lato, which we think is very important because when you want to play with the Lato, there are 3 phases. The first that starts it, then the lower phase, the reporter described very well, and then the higher phase, when the balls are also bouncing on the top, where the reporter did quite a good job of describing, because the feedback is needed. But the opponent had made some flaws in our opinion, because there was some, in our opinion, too much focus on the damping, which is not that interesting in this system, and the natural frequency. So let's move on to the discussion, which clarified a lot of stuff. First, the discussion about the experimental setup that clarified how the setup worked, which wasn't really in the presentation described as much. Then there was another clarification with the amplitude investigation, and then they discussed the second mode transition, which they agreed that it is hard to do using a machine, but by hand it is possible, because you need to change the amplitude of the Lato quite a bit. But they discussed, for example, the chaos in the system, which we think is not really interesting, and the time could be spent better. So the dependence on the initial condition. The reporter said that the system is not that the stabilized frequency is not depending on the initial condition, but we think it is dependent with the initial conditions, because for example, for too small initial condition, the system can dump down, and for larger, it can stabilize. Then the string slacking, from the video, we agree with the reporter that the string wasn't slacking, but it was a wave, but the important thing is that the Lato had to collide at the same height to not create the slacking.
Yeah, concluding remarks.
So thank you for the reviewer and the opponent for the discussion. First, I would like to summarize my report. So for the key mechanism of the system is the parametric resonance and with the modulated gravity. We have found a numerical solution considering the collision and effective gravity. We investigated the parameters including the frequency of the pivot and the length of the string. However, I did not investigate the pivot or the amplitude of the ball experimentally due to the problem statement not mentioning the parameters, so I chose to focus on the phenomena explanations. And we have also found a hysteresis present for a dynamical frequency change. which I believe is caused by the initial condition. But however, I don't think that the initial condition will change the final stable state frequency or the stable state amplitude, as the opponent or the reviewer had mentioned. You will only change the process to get to the stable state, or whether you will get to the stable state or not. And the stable state frequency will equate to the driving frequency. And we have a slope equals 1 with the frequency, two frequency graphs, and it will only be possible for the string. And the other possible steady states are only possible with the rigid state. And I believe that a phase transition to double collision will need a pivot sudden amplitude increase downwards. So for the discussion, we have separately characterized viscous damping and collision as we have clarified with the opponent. And the string stacking condition is considered through relative acceleration, causing a phase transition. We have actually accounted for using this equation, which we can also characterize the condition on how much we should increase the amplitude. However, I think that if we're playing with our hands, it is not relevant. And we have also clarified that the initiation is caused by string wave. When we oscillate it, you'll have little waves, and they will be pushing it into each other and causing an initial perturbation. And I want to clarify there is no chaos in the system. Thank you.
Your questions, who wants to go first? Yes.
Can you go to the hysteresis graph, please?
Meanwhile, if you have a good question.
Question to the reviewer. You were pointing out that there could be a torsion due to the elasticity of the string. How would it influence the effect quantitatively or at least qualitatively?
When the torsion of the string happens, the balls start to spin, and when the spinning balls collide, it adds to the system the further dimension.
Yes, thank you.
Okay, thank you.
You shut down for no reason.
the project there is shut
Okay.
down.
Just let's pause the time. Because I have a question and I need to as well. Let's not ask questions until we figure the project thing.
You just press that one.
Maybe continue with the question to the opponent.
And then then
Okay.
it might be unfair that someone might then the opponents and the reviewers might get too many questions and the reporter none. So let's just pause and wait for that. Meanwhile, I'll play with this. So. I'm not very clear.
Should we just connect to a smaller one instead? Should we connect?
Yes, you can do that. Yeah.
Is still the start.
Yeah. You can do that. And let's figure this out for the break. Just connect to the smaller one. I thought it would start.
Yeah.
Why is that shut down?
It's turning your screen. You have to duplicate the screen.
This start recording again? Okay.
And where is the HDMI cable? Thank you.
You had a question? You asked the reporter to go on graph, some graph.
I think it was.
It was
me,
okay,
yeah.
okay. Yeah, please start again.
Okay, when I'm on a frequency lower than the resonance, yes, can you explain to me why I can have increasing oscillation? Why is constant?
If you you're like oscillating it, not all the energy is inserted in. There is positive work and negative work. And apart from resonance, the negative work will cancel out the positive work done into the system, thus making a stable state not possible.
I have a question to the reporter. Like in the parametric instability case, it happens for some parameters, it doesn't for others. You have calculated functional relations, but is there a possibility like to poorly analytically calculate the conditions when the parametric instability happens?
Well, I believe no, because the theta is much larger than the small theta approximation. So there is a sine theta in the equation, thus making the analytical expression not possible.
Okay, thank you. No questions?
Maybe to the opponent, you were talking about the possible shift of the ball along the string. Do you think it has a relevant effect on the phenomenon?
So I do think that if it can move up, especially if it goes above the 90 degrees, so in phase or like the mode 2, if it starts colliding in, the string length changes because the center of mass of the pendulum moves.
Okay. Yes, please.
Yeah, maybe for the reporter, on maybe just a clear, short question. So you mentioned the Floquent modifier. Is it, yeah. Is this like a measure of chaos in the system, or could you?
It's a measure of non-linear dynamics. Okay. I think let me find my slide. It's a measurement of non-linear dynamics, which we can classify it as with orbital stabilities, where there will be like a limit cycle of a closed loop. So yes, we have calculated at SM0.7427.
Okay.
Yes.
Yeah, to the reviewer, you said about the rotation of the ball. So what's the effect of the rotation of the ball on the amplitude of it?
When the balls start rotating, it makes a qualitatively the Plato starts doing qualitatively different things. When one of the balls is rotating and they collide, they bounce into a different plane, and there the chaotic behavior starts happening. But we don't believe that it is important for this task, because when you play with the lato, everything is happening just in one plane.
Okay, thank you. I have a question to the reporter, saying about talking about like these two phases. I cannot reproduce it, but like when you're talking about when they hit it from the top,
Yes.
so when you resonate the amplitude even more. Does that require the amplitude change during the thing, or the frequency change?
No, it requires the amplitude change, because the string is initially a stacking. When it reaches more than 90 degrees, when it goes into like, it goes into
Okay.
this
Okay.
region.
Yeah, it's like, yeah, I understood. And maybe a question?
Can I have another one?
Yes.
You said that the initial conditions is not a relevant parameter. It's not relevant to your problem.
I think that I want to clarify. Just want to clarify the misunderstanding of the opponent, because they think that initial condition changes the stable state amplitude and frequency, and I don't think that is the case. It only changes how it gets into the stable state process.
So if I start from an initial angle higher than the angle of the stable state,
Yes, you will eventually
that
converge.
angle is not the maximum angle.
Just a short answer.
So the stable state will not be changed, because it will be smaller, and there is a stable equilibrium, steady state.
Thank you very much.
It's really fun.
I'm not talented. let's show the. Are you ready? Grades for the report. 8, 7, 8, 7, and 7. Grades for the opposition. 7, 6, 6, 7, and 7. And grades for the review. 6, 5, 7, 6, and 5. Thank you very much. Thank you. Yeah. So for the report, any of the sevens want to say something shortly? Yes, please.
Lato is a quite challenging problem, both theoretically and experimentally. The theoretical part you did quite excellent, but as the opponent showed us, there is a lack of data to compare it with your theoretical predictions, and therefore I had to give you a little less points than could be possible due to, I think you had a lot of experiments, but please show us them and try to compare it with your theory.
Okay. Thank you. For the higher end, I want to make a comment. So, I think that what regimes you have discussed and researched, and how you did it, different parametric resonances, how it happens, when it happens, the hysteresis process. Like there were some, no, not only one, but like more than one aspect that were like brilliant and scientifically interesting. So yeah, that's a really big pro. I probably would have considered going even higher if there have been like yes, the simulations were great and everything, but if there were some analytic expressions, I'm not like deducting any points because there were not, but of like with some simplifications of parametric resonance regimes and so on, maybe like I would have gone even higher. And also, I didn't go very high in the discussions, even though like you defended your results well. Yeah, I think you could have done much better job there as well to just to defend it more and explain what you did in your additional slides that you have not managed to present. So like overall, like every part of it was good, but I'm just giving some feedback of what when I would have given you a 9 or 10 or something like that. But yeah, your results I think were scientifically very interesting. Okay, let's move to the opponent. So we have six from Luis and Maroš. So either one of you should be good.
I can.
Yes, yes.
So yeah, for the opponent, I think he brought some interesting points, especially about like the string not being taught somewhere and stuff like that. But maybe what I deducted and colleagues didn't is for the start of the opposition speech, I felt that some of the report part was just a bit superficial, not much, but a bit superficial with statements like advanced equations and so on. But I like deeper activity. Just be careful to not fall into like aggressiveness.
Yeah. And higher end, we have 7th from Kenya.
Yeah, so I like the number of questions that were asked, the questions were asked, but as he has rightly pointed out, I would have given 8, but that aggressiveness where you have stopped him, he shouted basically at that point, and that's where you lost. So my partial grades were 1.2, 2.5, 2.5, which were 7.2, I will degrade to 7. for yourself.
Thank you very much. Yeah, I will also briefly comment. I liked your style of opposition. It was good. It is just a prioritization for me. Apart from that, like it was, I think you did what you should have done. Well, I don't think I fully agree with you what you said, but like whatever points you were bringing up, like it was valid. It has to be asked and discussed during the discussion. So like I liked your conduct, but yeah, I would have asked some things about like some interesting different regimes, hysteresis, and those kind of things that maybe like it's my point of view, but for me like those things were more interesting. So that's the only reason I didn't go high. And the review. We have from you, Luis.
Okay. We had a tennis physics fight with a lot of physics and a lot of discussion. And I think your reviewer was a little superficial about all the kind of stuff they bring to the topics. So this could be a 6, but I think was a little too superficial. I think it could be more things in our presentation. And for example, the conduction of they being rude, it could be, for example, in a slide or something.
And you have the high grade marks.
Yeah, so I partially agree with Luis that maybe the starting slides of the review were a bit bland, considering how rich was the presentation. But what I graded you highly, maybe that's why we differ, is the discussion analysis. I think that all the slides that you showed about the discussion analysis were adequate, and I also agreed with your statement as the reviewing team, so yeah, that's why I graded like 1.75 in the discussion analysis.
It was definitely a good review on standard IYPT level. Like you brought up some very good points, but yeah, there's some things were lacking in the review presentations, and although like whatever you said, you sounded like scientifically sound, and yeah, whatever you said, like I almost agree with everything, but yeah, you could have like reviewed much more of the process. So yeah, that's why I'm in the middle between the two. Okay. If you want to ask any partial grades from any juror, please do. If not, we can. Yeah. Thank you very much. Oh, it's 4:30 already. Okay, let's have a 7 minutes.